And your teacher is starting to need another haircut and a shave. Whoa. All right, moving on past the moon. Past the moon all the way to the sun. We're going to start looking at the sun, how it works. Let's get started. If you guys could write these questions down, we're going to come back to these in about a week or so. Hopefully you'll be able to answer them. But write them down, leave a space underneath each one so that you have room for the answer. Whenever you guys see something in this color, I'm going to need you guys to write this down in your science journal. Now, we've looked at something like this earlier, where Earth, next to all of the other planets, looks very, very tiny, especially next to the gas giants like Jupiter and Saturn. But if you put all of the planets to scale next to the sun, then Earth is absolutely minuscule. It is very, very tiny. All the planets are very tiny next to the sun. Earth, think of how big the Earth is, though, all the places that you could go and how long it would take you to get there. And now look at Earth next to the sun. Think of how big the sun must be if you were to try to travel around it. The weird thing, though, thing that blows my mind, is that if you put the sun next to some other stars, the sun is actually really tiny. There are some stars out there that are just huge. We're going to get into stars a little bit later in the year. We're going to look at different sizes of the stars. We're going to look at why some are the same color as the sun, while others are a different color. But the sun itself is just an average star. It's bigger than most, but there's definitely some that are quite bigger. Where is the sun located? Obviously, it's the center of our solar system. But when you look at the other stars in our galaxy, the sun is halfway out from the middle to the edge in a random spiral arm. There's really nothing special about where the sun is. It's not in the middle. It is not at the edge. It's just like in a random spot in our galaxy. So we have a pretty average star in an average location. There's really nothing special about where our sun is located within our galaxy. Are we the center of anything? No. The sun's not in the center of the galaxy. And Earth is not the center of our solar system. Florida is not the center of the Earth. You're not the center of anything. These are all in that pink, fuchsia, whatever you would like to call it, color. I would like you to pick two of them to write down. And immediately you're probably picking the two shortest, but I said two, so you get to decide. I'm going to go through each one of these. Sun's diameter across is 109 that of Earth. So you could fit 109 little planet Earths across the diameter of the sun. However, because that's just one dimension and volume is 3 dimensions, you get quite a bit more volume for every little bit that you get bigger. You get to actually fit over 1 million planet Earths inside of the sun. Think of how big Earth is. Think of how long it takes to drive just to Miami. Now think of how long it would take to swim to Italy. Think of how long it would take to fly to Beijing. Earth is huge, and you can fit 1 million of them inside of the sun. You guys already know that the average distance between the Earth and the sun is called an AU. How big is an AU? You could do almost 12,000 Earths lined up next to each other in order to bridge the gap between the sun and the Earth. 2 more facts. Your choice. The only reason the sun looks so big is because it is so close to us, but it's very average when you compare it to other stars. If it's so average, why do we spend time studying it? Well, it's the closest to us. It's the easiest to study. It's the easiest to see. We can actually send probes towards the sun. We can look at the sun in much more detail than any other star. So to figure out how stars form and work, the sun is what we're going to study. You guys already know that the sun provides heat and light to Earth. Outside of starlight, which is very minuscule, and radioactive decay, which produces some energy, some heat, all of the light that we have on planet Earth comes from the sun. The sun is why we have seasons. It's actually Earth's tilt in relation to the sun that gives us summer, winter, spring, and fall. Its gravity is what keeps the entire solar system together. It's what keeps Earth and Mars and Jupiter and Saturn and all of our planets and the asteroids and the Kuiper Belt and Oort cloud. It's what keeps all of us together as a big, happy solar system. Things that go on the sun's surface, which we'll talk about in a little bit, they can affect our climate, they can affect our atmosphere, They can affect our day-to-day lives, and we'll go over how all of those things can be affected by what's happening on the surface of the sun. Here's a question for you. Does the sun move? Well, that is a tricky question. The sun is relatively stationary at the center of our solar system. So if you want to say, does it move around in our solar system? Not really. Jupiter is big enough that it actually causes the sun to wobble just a little bit. However, the sun is moving around our Milky Way. It takes about 200,000 years for the sun to go around to orbit the center of the Milky Way one time, which means the last time the sun was in this spot in its orbit, dinosaurs were walking around. The sun also rotates. It spins. The center of the sun, what would be considered the equator of the sun, takes 25 days to rotate, and the poles take 35 days. You might think, how do they take different amount of times? The sun is not solid. The sun is a fluid. It's a plasma. So it doesn't all have to spin at the same speed. If the center takes 25 days to spin one time, and the poles take 35 days to rotate one time, which goes faster? Obviously, it's the center. All right, I want you to write down what's pink. The sun actually has a magnetic field very similar to Earth's, except the sun's is much, much stronger. This is a very important point. Because the sun does not rotate at the same speed in relation to the poles in the equator, they go at different speeds, the magnetic field lines actually get tangled. And if you take a look, you can see that it might have magnetic field lines looking very similar to Earth's, where you have a North Pole and a South Pole. But because the center of the sun is spinning faster than the poles are, these magnetic field lines are going to start to warp and they're going to bend. And as time goes on, these magnetic field lines get more and more warped, more and more bent, until eventually they snap back into place, but they've reversed. So every 11 years, the North Pole turns into the South Pole, and the South Pole turns into the North Pole. Because it is rotating at different speeds, those magnetic lines get very bent and warped until eventually they snap back into place, but they snap back in the opposite orientation, where the North Pole is now the South Pole and the South Pole is now the North Pole. It's then going to get all tangled again and get all warped again until 11 years later, the North and South Poles will flip, which means to go from the North Pole being at what we would consider the top, back to the North Pole being at the top, is a total of 22 years. But I want you to keep that 11 years in mind. That's going to come back, have an impact on what we're going to talk about in a bit. What's our sun made out of? Well, there's solid, liquid, gas, and plasma. Plasma is actually a superheated gas. If you know how solid, liquids, and gases work, solids are very still. The molecules do not have a lot of kinetic energy. You get a little bit more kinetic energy, and the molecules can move around and slide past one another. That's when you're a liquid. If you have a lot of kinetic energy, by adding in more heat, you can actually have the molecules of that substance bouncing around and flying apart. That's a gas. If you continue to add heat, they speed up, and they are moving around so fast that those electrons in the outer levels, valence levels, actually get stripped away. And if you don't have electrons and you're stuck with your protons, you have a charge. You have your protons, no electrons, you're going to have a positive charge. So plasma is a superheated gas that has a positive electric charge. The sun has a positive electromagnetic charge. Electromagnetic. It would make sense that there is a magnetic field on the sun because it's made out of charged particles. What are those particles? About 72 to 73% of them are hydrogen. Just one single proton. Remember that there's no electrons. The electrons are just flying around. They're not attached to the protons. So you just have a bunch of protons flying around. That's hydrogen. About 25% is helium, which is what is being produced. So as time goes on, the amount of hydrogen is going down and the amount of helium is going up because we're taking hydrogen and turning it into helium. We'll get to that in the next lesson. And then about 2 to 3% are other materials. So when I say other materials, I mean everything else. You can find gold in the sun. You can find carbon in the sun. You can find oxygen in the sun. You can find arsenic. You can find calcium. Any element that you can see on the periodic table up to 92, uranium, is in the sun. How did it get there? The sun is what we would consider a second or third generation star, which means there were stars that existed before it that have already died. And when some stars die, they produce those heavier elements in a supernova. They're going to spread those throughout the universe until eventually they recoalesce into a new star. As that happens more and more often, you're going to make more and more of those heavy elements, things like titanium or gold or silver. Later generations of stars will have a higher percentage of those heavy elements. Our sun, we estimate, is about a third generation star, which means a star has lived its life, exploded, another star coalesced all of that material, lived its life, exploded, and now the sun has all of that material and is living its life. There are a few elements that don't exist in the sun, things like francium or vanadium. Those elements have very short half-lives, which means they are radioactive and they decay into other elements very quickly. The sun's been around for 4.5 billion years, so if you are an element that will radioactively decay in less than 4.5 billion years, there's none left in the sun. Here's a couple more things that I want you guys to write down. Its gravity keeps everything together. The energy from the sun sustains things on Earth. The sun makes up about 98% of all of the mass in our solar system. So if you added up every planet, every moon, every asteroid, everything in our solar system, it's only about 2%. The sun is made out of an ionized gas, easier to say plasma. Moving forward, if you do not know what radiation, convection, and conduction are, I want you to go to that link right there, and I want you to figure it out. I would also like you guys to make a sketch of the layers of the sun. There are 6 of them. I'm going to go from the innermost to the outermost. We have the core, we have the radiative zone, we have the convective zone, we have the photosphere, the chromosphere, and the corona. If your drawing does not look as good as this, maybe it looks like mine, that's completely okay. But I want you to make this drawing take up an entire page. Entire page. Don't make it small because you're going to be writing things inside of each layer. Maybe you want to draw something like this. Now that you have your sun drawn and you have space in each layer to write down some information, I want you to find some information. And I want you guys to write down the size of that layer in kilometers, not miles, but kilometers. What is happening there? So there's different things happening in the core than what's happening at the photosphere. There's something different happening in the radiative zone than the convective zone. Find out what's going on. What's the temperature range for each one of these layers? And then find one other fact about each of those 6 layers. The core, the radiative zone, convective zone, the photosphere, chromosphere, and the corona.